Figure 14.26a shows a spring of force constant K clamped rigidly at one end and a mass M is attached to its free end. A force F applied at the free end stretches the spring. Figure 14.26p shows the same spring with both ends free and attached to a mass M at either end. Each end of the spring in figure 14.26p is stretched by the same force F. So we are given the two figures here, the figure A and figure B. In figure A mass M is attached to a spring of force constant K and an external force F is applied to this block of mass M. And in figure B, two masses of each of mass M are connected to the same spring of force constant K, and on the both sides of mass M, on both of these blocks, a force F is applied. So these are the two given situations, and what we need to calculate is what is the maximum extension of the spring in the two cases. So problem is pretty much simple. We need to calculate the maximum extension in the two cases. If I consider case 1, when I apply an external force F on the block, this spring gets extended, the spring gets stretched, and in the equilibrium position, when the extension is maximum, suppose say maximum extension is X max, and in equilibrium F should be, that is external force, should be equal in magnitude to the restoring force, which is K times the X max. X max is the maximum displacement. This implies X max is equal to applied force F by the force constant K. Now coming to the second situation, if I consider the maximum displacement X max here for both the blocks and a force of restoring force is acting on both the blocks, again I get F is equal to M times X max. This implies again I get the value of X max to be, sorry, this is K times the X max. Because restoring force is equal to spring constant into the displacement, which gets equal with the applied external force in magnitude in equilibrium. This implies X max is equal to F by K, which is same as in figure A. Now in the part B, we are asked to calculate the period of oscillation in each case. If we consider figure A, we know the standard formula for the time period of oscillation is 2 pi under root m by k. And for the second case, if I talk about the time period, so time period will be 2 pi divided by m by 2k. Now the question arises, from where does this 2k comes from? If we consider the problem and we consider the system of two masses as a system, we see that net external force acting on the complete system is 0, so center of mass of the system remains at rest. Suppose if this is the center of mass of system, this is the center of mass of the system. This center of mass of system remains at rest and each block oscillates about this center of mass. And equivalently, we can consider a mass attached to a spring of length L by 2, and force constant 2k is oscillating about this point. So we can get the time period of oscillation of each block to be 2 pi root m by 2k.